Hey, Alan. I've been following your project a little here for creating a bouncing ball on the Coco tech screen and thought it was a great little demo that you had been working on. And I noticed that you reached out to the community asking if folks had an idea on how to possibly implement gravity. I believe in your demo you were trying to use a increased value of 0.25%, 25% each time the ball moves in the y direction. But after giving it a little bit of thought, since the demo itself is somewhat static, there's no interactive components. People aren't, using any type of input to impart any force on the ball or anything like that. Good way to do this might be to use a lookup table to handle the gravity. And as an example, I used lookup table on Run Dino Run for when the little dinosaur jumps. All the jump frames are being used or being looked up through the lookup table. So the nice thing about using this method is there's no calculations needed during the code execution, and it makes it extremely fast and compact. It's a nice way to handle the gravity effect. So let's take a look at this and figure out what might be a good way to implement this. So let's bring up your code first, and it looks like here's the most recent version that you had of it using the constant value of adding 25%, and we'll give that a quick run. And as you can see, as you mentioned, it's not quite making it to the bottom of the screen. So how would we approach this? So in order to create the lookup table, we need to know which values, what our boundaries are of what we're trying to work with. So looking at the Coco tech screen, we can kind of think of it as we go from 0 to 32 in the horizontal direction, and then 0 to 31 in the horizontal direction, and then 0 to 15 in the vertical direction. So we can kind of think of that as 32. We'll use the metric system here, make it a little bit easier. 32 meters wide and then 16 meters high. So let's build a worksheet to calculate these values. So I'll pull this up here, expand that a little bit. And what I've got here to calculate the values is just basically the equation for an object in free fall. Here we initially start with distance as a function of time. That is, we're trying to figure out what the distance fallen is based on how long it's been falling. And the values that we have here are d for distance, or we can think of that as our vertical y-axis. Then we have 1/2 gt squared, g being the free fall constant, gravity, 9.8 meters per second squared, and t is our time in seconds. And as we iterate through time, it grows by a factor of 2, so it goes pretty quick the longer it goes. So let's set up a few variables here. So what we'll do is we'll say that our gravitational constant is 9.8, and I'll put some units on there, so meters per second squared. And then we'll just calculate what our time length is for it to fall a set distance, and that set distance for setting up our boundaries will initially start at 0, which is the top of the screen, and then the bottom of the screen we can think of that as a total height of 16 meters. So the bottom of the screen, we want it to bounce when it hits that point, so we'll set that at 16 meters. And from there, what we can do is we can calculate t, our time value, for how long it's taken to fall that far. And to do that, we can just solve for t, and we take our initial equation here. We have this 1/2 component where we can get rid of that by multiplying both sides by 2. So with that, we're left with 2d equals gt squared. Then what we can do is we can divide both sides by g. So we take the g, move it from here, and divide over here. So 2d over g is equal to t squared. And then to solve for t, we can just take the square root of both sides. So we're left with t equals square root of 2d all over g. And that'll give us how long it takes for an object to fall a set distance. So going back to our equation here, or our variables here, we want to see how long it takes to fall that 16 meters. So what we can do is we can solve for t by going square root of 2 times our distance fallen, which is the C2 value, and that's divided by our constant of g, in this case the 9.8 meters per second squared. And from there we're left with 1.8 seconds. So basically what this amounts to is in order for it to fall that 16 meters, or that full 16 vertical points on the text screen, it's about 1.8 seconds. So next I'm going to build our lookup table, and to do that we'll just set up a little sheet here to calculate that. So we'll use t as the total time fallen and d as the distance fallen. We'll start at 0, and to calculate for the distance fallen we go back up to our initial equation where d equals 1/2 gt squared. So d is going to be equal to 0.5, we'll get that out of the way, 0.5 times g, which is $C $2 1, sorry about that, times our t component squared, which is just going to be this value right here. So we do times a6 to the power of 2. And obviously at point 0, time equals 0, the distance fallen is equal 0. We're still at the top of the screen. So the next thing I want to do is we want to go all the way up to 1.8 seconds here, which is going to be our maximum value. So we'll drop this down. Oops, we have to set up an increment value. So I'm going to say we'll do by values of 0.1 to start. We'll see what that looks like. So we'll drop that down, maybe about there. That's a little bit too far. So we've got 0 to 1.8 seconds there. Next thing I can do is drop our calculation down, and as you can see, at 1.8 seconds it's fallen just about that 16 meter length, and you can see each one of these iterations, it gets a little bit faster each time, or a little bit further each time, and it's obviously falling faster because the rate's increasing. So one other thing I want to do, because obviously with the basic Cocoa text screen, it's using integer values, so we want to get rid of these decimal places. We can't use floating point. So I'm going to do d truncated value. And for that, we're just going to do equals to truncate. This will help to save time in our calculations as well in the basic code. If we have this done ahead of time, we don't have to convert from floating point to integer in the code. We can do it right here. So we'll do B6. I think that's right. And obviously 0 truncated to 0, 0. We'll drop that down. And what we're left here is values that go from 0 to 15. And that actually works out nicely for us because it's a total of 16 values. So we can think of the topmost line in our Cocoa character screen as line 0, going all the ways up to Y value of 15. Then the next thing I want to do is take and, just to save some time, convert these values to some sort of form that we can use in our basic code. And rather than do it manually, I'm just going to try to generate somewhat our data statements in the spreadsheet here. So I need to convert these to text values. So I'll do text C6, and it's just basically a number format. So our first value, it's going to be blank, so that's why you don't see anything there. And then what I want to do is take this value and add it to the next one, and so on. So we iterate through, and it grows longer each time. So I'm going to use a concatenate function here, and we're going to do D6. We're going to use a comma as a separator. And then the next value is going to be this one over here hidden behind our formula, which is going to be, well, we got to convert that one to text as well, C7. And again, we'll use the number format there, close parens on each, and we've got just the comma there. So that's basically 0, comma 0. So what we'll do is we'll just manually fill in those 0 values. So there we've got it populated. Just to make it a little bit easier, see, we'll do a left justification on that. So there's our values for our lookup table. So one thing to consider here also is this is just us dropping the ball and it reaching to the bottom of the screen, and we need to calculate what's going to happen as it bounces back up to the top of the screen. And with no other forces on the ball, there's no friction or anything else, there's no heat loss when it bounces, it's just going to be exactly the same. So all the energy that was put into the bounce going down is going to be the same for it going back up. So these values are just going to repeat in the other direction. And an easy way to do this is we can just say, all right, let's start it going back up here at 1.7. We'll drag this down until we get to 0. One more. There we go, we're back up to 0. Actually, I'm going to leave this one off. We don't need to do that twice. And from there, what we can do is we can drag these down, our calculations down. And there we go. So that right there we can use as our data statement. And again, we're just going to have to manually fill in the zeros. We'll just live with that. So what I'll do is I'll go ahead and copy this. And we'll take that back over to our basic code. And what I'm going to do here is I'll just set up, I've got auto line number turned on, so I'm just going to go to 200. And I'm going to set up a lookup table here. I'm just going to create an array with a certain number of values. So actually what we'll do is 200, the number of y values, not sure what that is yet, but we'll do 300 as our data statement, and we'll insert our values there. So again, change these zeros, these blanks to zeros. And one other thing that I'm going to want to do here is I'm going to want to have a terminator at the end, so we know once we've gotten to the end that we're there and that we need to start over from the beginning. And easy way to do that is just kind of use something that you wouldn't normally encounter in your lookup table. So I'm just going to use a -1. So we know that if we encounter a negative value, that basically we are at the end of our lookup table and that we should go back to the beginning. So let's see how many values we've got here. I could count them out, but I'll just do it in Excel and have it count them for me. So it looks like we've got a total of 36. So number of y values equals 36. And then from there, what I'll do is we'll set up our lookup table. So we'll do dimension, the number of y values by the number of y, 220 for, and we just need to set up a for loop here. So we go from 0 to the number of y values, and we'll read y. Oops. I have auto capitalization turned on, so I keep hitting shift to try to do caps. X, and then we do next, and then we'll return from our subroutine here. So up here, what I want to do is we can do this after our CLS. We'll go sub 200 to our routine for reading in our table, and I just want to make sure that works okay, that we're getting all the values. So we're out of data, so I need, let's see, so we're one beyond, so we actually need to change this to 35. I forgot to subtract one off, so that's good there. And there we go. So the ball is still bouncing. We haven't changed any values there for how that ball actually uses the lookup table. So we'll do that right now. So next what we want to do is modify the code a little bit. Instead of starting x at 1, I'm going to start that at 0. Y is going to start at y0. so our first value in our lookup table here. XM is going to be equal to 1. YM, going to change that to 0. From there, looks like this is okay. We're not going to change anything in the x-axis, so everything stays the same there. If it is less than 1, we're good, and if it's more than 31, we're good. So we're just going to change it to, we're just going to invert it there. Okay, so what we're going to change, however, we can go ahead and get rid of this line 70. We're not going to need that any longer. So for the y values, what we're going to do is we'll say ym is equal to ym plus 1. So we increment our y movement counter. And then beyond that, we no longer have to do a check to see if we're in still within the boundaries, because our lookup table is going to confine those boundaries. We'll say y is equal to y times our sub-value ym. So this is where we're actually doing our lookup. We first increment our lookup table through each value here, and then we actually grab our y value from the lookup table. But what we do need to do is see if we've hit this -1 here. So if our y that we pull out of our lookup table is less than 0, then we can say ym is equal to 0. So we're just resetting our lookup table, and we'll say y is equal to ym again. So we'll need to do another lookup to get rid of that -1 value. Oops. And I believe that'll do it. So let's take a look and see what that looks like. There we go. It looks good. So it looks like we've got some gravity there, and it is bouncing, and it's staying up at the top a little bit longer through those 0 values, and then falling further each time. It does look a little bit slow to me, so what I think I might want to do, and we've got a bug there. It looks like what's happening is quite possibly if we hit the value of y, or let's pull this off to the side here. If we hit a value of p equals 511, which definitely can happen, what's happening is it hits this point here. It'll scroll up once for printing the blank space, and then it'll scroll up another time for putting the 0 on there, or actually the reverse of that. So it'll print the O, and then the next iteration through, it'll print blank space. So it's scrolling up. But we'll take a look at that in just a second to see if we can get rid of that. So first thing we're going to do is try to speed this up a little bit and decrease the number of values in our lookup table, which is essentially increasing how fast the ball will be going. So we'll minimize this, and instead of incrementing by 0.1 seconds, what we'll do is we'll increment by 0.2 seconds. So everything can stay the same. We can just drag that down, and we want to again get to 1.8, so that's going to be about halfway. So we'll see what that looks like. So it's a little bit further. We'll change this to 1.6, and we want to go back to 0. And one more. Oops. Bring it back down to 0. There we go. Everything else below this we can get rid of just to get it out of the way. Okay, so let's take a look to see how many values we have here now. So it's 19. 19 values, 24 minus 6 plus 1 is 19. So we'll go ahead and copy this. Go back to our code. So we'll go ahead and get rid of that. We'll replace it with our new values. And what we want to do is change again these two zeros. The -1 on the end. And we said that we were at 19. So what we actually want to do is change that to -1, 18. So 0 to 18 gives us our 19 values. So we'll change that to our 18 values and see what this looks like. And there we go. The ball is definitely bouncing faster. Obviously, there's less frames there, but that's where we're getting the speed increase from. So looks good, and there we've got the artifact where we're hitting a p-value of 511 and it's scrolling up twice. Let's see how many times it actually does that. I'll probably keep doing it eventually. Looks pretty good though. It's definitely showing where it's spending more time at the top and it's falling dramatically faster as it gets towards the bottom. And there we go, it hit it again. So one way that we can get rid of that, I know that we're using the print at here. Instead of using the print at, what we can do is, and I don't think you'll need to do this, Alan, in your demo, because I believe, let's take a look at your code for the ball itself. Part 4. Yeah, so it looks like what you're doing is these values here will never actually get to the end of the screen. The bottom of the ball will never actually get to the edge of the screen. So you should be okay. Continue to use the print at. But for the purposes of this exercise, what I'm going to do is change this to poke statements because the poke won't scroll the screen for us. So the beginning of the text screen is value 400, hex value 400, and H plus P, and we'll use 96 for a blank. P is equal to our x plus y times value of 32, which is hex 20. Keep doing the lowercase, and then we'll poke our y value, or our o value, and we do 1024 plus p, comma, and the ASCII for that 78. Let's try that, see what that looks like. Nope, it's an N. So oh, I went one. So it should be 79. NOP. There we go. And there we go. So we've got our little bouncing ball. We shouldn't get that artifact once it hits 511. Give it a couple more tries. There we go, and it did. We did see it hit the bottom corner there, and it didn't scroll. So there's our little bouncing ball, and then we can take this algorithm, this lookup table, and the values that we calculated, and transfer those to the bouncing ball itself. The only difference is, obviously, with this O, it's a single character, so we've got the full 16 values in the y-axis. The ball itself is a little bit bigger, so we need to take that into consideration, and we need to calculate that from the bottom of the ball. So our values are actually going to start probably somewhere around here, depending on how tall the ball is, and then from there we can go to the bottom of the screen with the ball. The effect might not be as dramatic because the ball is kind of large, but we'll give that a shot in some other video or some other iteration of the test. All right, this has been fun to play with. Hopefully it's something that folks can learn from and works for you guys. All right, take care. Thanks, Alan. Bye.